In this work, we present TacScope, a miniaturized vision-based tactile sensor for surgical applications. We will discuss TacScope's sensor design, key characteristics, and 3D depth reconstruction method. We will also present its applications, including artificial tumor detection, tumor shape classification, and surgical scenario validation. TacScope is designed for compactness, making it ideal for surgical applications. It has a 7 mm physical diameter and a 5 mm sensing region. Here, we present the exploded and cross-sectional views of TacScope, highlighting its three main modules: perception module, optical module, and contact module. The perception module consists of a miniaturized camera and an LED ring for visual sensing. The optical module includes a soft silicon lens and a sensor shell for lens housing. The contact module is made up of three layers: a particle layer, a transmissive layer, and an absorptive layer. TacScope's tactile response relies on ink particle redistribution under pressure. Higher stress causes greater dispersion, exposing the gray absorptive layer, creating contrast variations in tactile images for precise deformation mapping. Here, we demonstrate the optical characteristics of TacScope. The camera operates within a working distance of 5 to 10 cm, and our custom-designed silicon lens allows it to focus at just 10 mm from the image sensor, ensuring clear tactile imaging. To evaluate resolution, we use the USAF 1951 test target. TacScope successfully differentiates Group 4, Element 2, corresponding to a resolution of 55 microns. Additionally, we present the optical path difference plot, which provides insights into the lens performance. In the OPD plot, the vertical axis denoted by W represents total wavefront aberration, and the horizontal axis denoted by rho Y and rho X represents tangential and sagittal ray height on the entrance pupil of the sensor. The OPD plot shows the presence of aberration near the periphery of the entrance pupil of the sensor. Here, we present the tactile resolution of the sensor. TacScope is capable of resolving tactile imprints as small as 0.25 mm. Here, we present examples of 3D shape reconstruction using TacScope. From top to bottom, we show visual images, TacScope signals, difference images, and inferred depth for a sphere, hemisphere, screw thread, triangular frustum, and hexagonal Allen key. TacScope accurately estimates 3D depth with high fidelity. Here, we demonstrate TacScope's real-time 3D depth reconstruction through experimental validation. Various objects were pressed against the sensor's tactile surface, and their inferred 3D depth was visualized. For this demonstration, we used a triangular screwdriver bit, a Torx screwdriver bit, a hexagonal Allen key, a screw thread, and a sphere. The results confirm TacScope's high accuracy in detecting depth variations, highlighting its effectiveness in precise tactile sensing. Here we present the quantitative analysis of 3D depth reconstruction accuracy for 5 object shapes: sphere, hemisphere, hexagon, triangular frustum, and cylinder. Each box plot illustrates the point-to-point error after iterative closest point alignment, with the green triangle marking the mean error. On average, TacScope achieved a mean absolute error of 0.1468 mm and a standard deviation of 0.1057 mm, demonstrating sub-millimeter accuracy across all tested geometries. Here, we have validated TacScope's capability through a tumor detection experiment. We simulated tumors by embedding metal spheres of 2 mm, 4 mm, and 6 mm diameters at depths ranging from 1 mm to 5 mm within a phantom material. The sensor was mounted on a CNC machine and pressed against the phantom skin, applying a maximum force of 1,500 grams to mimic human palpation. 2 phantom types were used: positive samples with embedded tumors and negative samples without any tumor, subjected to forces between 1,000 grams and 2,000 grams to introduce tactile variation. Here we present demonstrations of tumor detection using TacScope in real time. During these demonstrations, dummy tumors were placed at depths of 1 mm and 5 mm beneath the phantom skin. We used a ResNet classifier to distinguish between positive and negative samples. The model achieves 100% accuracy on both training and test sets, proving TacScope's effectiveness in detecting tumors. Additionally, we reconstructed tumor shapes beneath the phantom skin from the tactile feedback, further enhancing detection capabilities. These results highlight TacScope's potential for robot-assisted, minimally invasive surgery, providing real-time tactile feedback for more precise interventions. To evaluate TacScope under more clinically realistic conditions, we tested it on soft silicone phantoms embedded with tumors of varying stiffness achieved by mixing different silicone compounds. Here we show A. The data collection system mounted on a CNC bed. B. Soft phantoms with embedded tumors, increasing in stiffness from left to right. C. Raw tactile feedback from the sensor, revealing subtle particle shifts due to soft tumors. D. A 3D reconstruction of the deformed tumor after contact. TacScope achieved 96% accuracy in detecting soft tumors at a shallow depth of 2 mm, demonstrating its sensitivity to subtle mechanical changes in tissue. In our second experiment, we evaluated TacScope's ability to classify tumor shapes, including frustum, hemisphere, sphere, and ridge structure. Each phantom had an additional silicone layer of varying thicknesses, 0 mm, 2 mm, 4 mm, and 6 mm on top of the embedded shape. The sensor was pressed until a clear tactile imprint was captured. The setup and tumor structures used in this experiment are shown here. Here we present some demonstrations of tumor shape classification using TacScope in real time. During these demonstrations, dummy tumors of different shapes were placed at a depth of 2 mm beneath the phantom skin. We trained 4 separate ResNet models to classify tumor shapes at depths of 0 mm, 2 mm, 4 mm, and 6 mm. The classification accuracy is shown here with a grouped bar chart comparing performance across depths and tumor shapes. Additionally, confusion matrices provide a detailed performance breakdown. TacScope successfully classifies tumor shapes with high accuracy. This capability enhances the sensor's utility in distinguishing different types of tumors in minimally invasive procedures. Finally, to validate TacScope in a realistic surgical setting, we conducted tests using a soft phantom with an embedded tumor placed inside a full-size mannequin. A small incision was made to mimic the limited access of minimally invasive surgery. The TacScope sensor, mounted on a UR5E robotic arm, was inserted through the opening, as shown here. Data were collected under restricted space and visibility conditions. We acquired 60 tactile samples, 30 from tumor regions and 30 from healthy areas. These were not used during training. The pre-trained classifier was tested directly and achieved an accuracy of 96.67%. Here, we demonstrate examples of operating the sensor in a simulated surgical environment. On the left, we palpate tumorous tissue, and the sensor successfully detects the tumor upon contact. On the right, we palpate healthy tissue, and as expected, there is no indication of a tumor, even after palpation. In summary, TacScope delivers high-resolution tactile sensing, accurate 3D depth reconstruction, and reliable tumor detection and classification. Thank you.